Thank you, everybody. I really would like to thank you for participating, in this webinar. So let me quickly start with our introduction first. Myself, Sadaf, and I work as an account manager in Detroit Engineered Products. And along with me, I have Yusuf, okay, from our technical team. He will be driving our main topics of the webinar today. Okay, so before we deep dive into our webinar topics, I just would like to talk about our agenda first. Okay, so this is the agenda that we are going to cover today. Introduction we already covered, and I'm going to take at least 5-10 minutes so that many of you, might not be familiar with what DEP does. Okay, so I'm going to take 5-10 minutes where I can talk about as a company overview, and then I will hand over the call to Yusuf, who would talk about the listed webinar topics for battery thermal runaway. Okay, and from this webinar, we are going to discuss about some of the key takeaways from this, two topics. Okay, and if time permits, we can also talk about the further engagement models. And we are going to also reserve 5 minutes for questions and answer. But in case you have any questions in between, you can drop your questions in the chat, and we can end up pick those during the Q&A. Okay, so let me start. Okay, so DEP stands for Detroit Engineered Products. We are a 25-year-old company. We started in 1998 as a software company. We started as a software company. We have our own in-house CAE software that is competitive to ANSA or HyperMesh. Okay, many of you might know this software. Okay, so as of today, we have 4 business units, as you can see. Engineering consulting, where we do all types of turnkey engagements, ODC engagements for design and engineering. So all the way from design, CAE, all the engagements related to battery applications, automotive, non-automotive, doing all control systems, embedded systems, software development, comes under this division. Secondly, we have our software division. As I mentioned, we have our own CE software, okay, that is called Meshworks. We sell the software to customers, and we also deploy it at their locations. Then product development, where we support companies in innovative products. Okay, so here we provide complete end-to-end product development support, right from designing the concept to prototyping. I will be emphasizing more on this product development division in the upcoming slide, as our thermal runaway sensor, is also part of this DEP Innovent division. Okay. And then talent acquisition. So here we place people on contract if you need any battery engineer, thermal engineer, software engineers, embedded engineers, for short-term, long-term contracts. We can, provide those engineers at customer locations globally. Okay, so currently we supply these type of resources, okay, to many battery companies, OEM, Tier 1 suppliers. So when it comes to our global team, we are headquartered in Troy, Michigan. We have offices in California, Brazil, and 2 offices in India, Chennai and Bangalore. They serve our low-cost design and engineering center. And additionally, we have offices in Tokyo, Japan, and Shanghai, China. So whatever you see in this map, okay, the fonts highlighted in red, those are our own offices, and all the blue font, such as Germany, Italy, Poland, France. Okay, we work with our partners, and these partners they sell our softwares and services in these geographies. So when it comes to the verticals, we support a wide range of verticals. Okay, but our primary focus is on the automotive, which is responsible for 70 to 80% of our revenue. However, we do have other customers in aerospace, consumer electronics, biomedical, heavy engineering. Okay, so we support all engineering verticals. Okay, and if I talk about our global team member, okay, so we are 550 plus, globally as an employee strength, and out of these, 65% are dedicated to engineering and design, handling a lot of turnkey projects, ODC engagements for customers, as I mentioned earlier. Okay, and around 20-25% they are on the software side. So we have a good mix of cross-functional engineering team. Okay, comprises of mechanical, electrical, electronics, and software engineers. And we have almost like 20%. They're coming from PhD background, specializing in areas such as CFD, high computing thermal analysis. Okay, as we know that, okay, battery being a very specialized area. Okay, we need very niche level expertise here. Okay, so that's why we have a team structure, and 70% they have master degrees, and 10% they have bachelor degrees. So when it comes to the overall services, okay, we proudly say that, okay, we are a one-stop service provider for our customers. Okay, I mean, we can assist you from product ideation to creating concept for your product, detailed design engineering, and all kinds of system engineering and mechatronics support. Okay, and we do have capabilities, all the way from developing control systems, whether it is engine control, powertrain control, chassis control, infotainment, doing all the software integration. Okay, and at our Troy office, okay, I mean, we also support benchmarking. Okay, for any of your competitive products. So we have a dedicated lab at our Troy office specifically for benchmarking. Okay, so here we tear down all the components. We scan the components. Okay, I mean, no matter how big or small. Okay, from the scan data, okay, we can generate all the 3D model, and from the 3D model, okay, we can perform all the CE simulations, performance simulations. And one of the core expertise of DEP is, we are also heavily involved in the lightweighting and optimization projects. Okay, so such as any value engineering projects. Okay, when customer asks us, to optimize their design to achieve their weight reduction, or probably, it could be, they would like to use some alternate part design without compromising the performance. So all the way from stamp structures, BIW, aluminum castings. Okay, all the way from plastics, interior, exterior. We have very good experience. Okay. So this slide, okay, I mean, covers a wide range of services. Okay, so like I said, okay, we can proudly say that we could be your one-stop service provider for any of your design and engineering needs, that you can count on us. So I'm just going to quickly, touch base a few more slides. Okay, just talking more about as a company background, and then I will hand over it to Yusuf. Okay, because I think that would be more interest to you guys. Okay, and in the EV area, okay, we are very strong. As we know that, okay, I mean, the entire automotive world, okay, is shifting to electrification, and that is the reason we also invested heavily in this area. Okay, so we can proudly say that we are working with almost every second or third EV company in North America. Okay, so and then we provide extensive support to all these companies, EV companies. Okay, so sometimes I mean, we support them at component level, sometime at their subsystem level, and or sometime probably like for their entire vehicle. Okay, including BIW, chassis, powertrain, battery, control systems. Okay, so this slide pretty much talks about the depth of our experience in the EV domain. Okay, and we are supporting our customers either designing their EV vehicle from the scratch, or converting their IC vehicle, to an EV vehicle. Okay, so all the way, from system level modeling, meeting all their speed requirements, performance requirements. Okay, I mean, we use all the MATLAB simulating, okay, to designing their battery, determining what battery size they would need, motor side, doing all the battery simulations, for cell level, module level, pack level integration. Okay, to the vehicle. Okay, and also, on the when I talk about design and integration, okay, we do support all the control systems, power electronics, wiring harness, both for high voltage and low voltage. Okay, so this is just a quick summary, about our experience in the EV sector. Okay, so here I just would like to take another minute, and then I'll hand over the call to Yusuf. Okay, so this particular slide, I mean, it talks about our core expertise in product development area. Okay, on the right hand side, you can see images of our in-house development, which support multiple product development activities. Okay, I mean, we have designed and built our own EV scooter. Okay, electric power tools, drones, and ion combustion sensor. Okay, these are just few example. Okay, okay. So we had worked, both in-house technologies as well. Okay, to demonstrate what capabilities we have, and how serious we are when it comes to the product development. And there are n number of product development. Okay, in collaboration with customers, we have supported them. Okay, so overall, this slides highlights our capabilities all the way from electromechanical product design and development. As I mentioned earlier, we can handle everything from mechanical design, electrical integration, sensors, controls development, prototyping, bench testing, and so on. Okay. So, so I think with that, I completed the DEP background. Okay, and I can request Yusuf to take the control, and he can start with the webinar topics then. Thank you.
Thank you, Siddharth. Hi, everyone. So welcome again to the webinar. My name is Yusuf Mansour, and I'm a mechanical engineer. I've been at this company, DEP, for about 5 years, and in this time, I've been developing our spark plug and glow plug sensors, and I am the project lead in the development of this thermal runaway sensor. So we're going to go ahead with the agenda. So today we're going to go through 2 topics. Understanding thermal runaway is topic A. We're going to go into triggers, battery safety, the stages of thermal runaway. And then we're going to introduce our technology. So we're going to go into the basics of the sensor and how it works, and the testing video and the results of our tests. So starting with thermal runaway, understanding thermal runaway, the definition would be like thermal runaway is the propagating exothermic reaction that a battery undergoes, leading to dangerous situations if not mitigated properly. Now, here I have a list of triggers to thermal runaway. So there is temperature increase, physical damage, overcharging, manufacturing flaw, and excessive usage. Now, beginning with temperature increase, this can lead to atmospheric condition. It can be due to atmospheric conditions, or it can result from other triggers. So, and the increase of the temperature results in the melting of the separator between the anode and the cathode, and that creates a short circuit. Now, physical damage can be due to punctures or deformations, typically from vehicle crashes, and these can result from the battery short-circuiting internally or externally. We have overcharging and excessive usage. Both of these can heat the battery, resulting in an internal short circuit in the similar way that the temperature increase trigger does. Now, in a manufacturing flaw, it's a rare scenario, but it is possible. It can cause an internal short circuit in the battery, even during normal operations. Now, these manufacturing flaws can be due to many things, for example, debris or impurities in the battery itself in the process of manufacturing. Now, all of these internal short circuits and all of these triggers, they can ramp up the temperature even more and propagate to other cells, causing thermal runaway. Now, thermal runaway can lead to safety issues. Failure to mitigate thermal runaway can result in the battery producing toxic gas and other harmful chemicals into the atmosphere. So any bystanders or passengers in the vicinity can inhale these hazardous gases, causing them harm. Now, these same toxic gases are flammable, and the heat generated from the thermal runaway can cause the battery's electrolyte to combust or explode, resulting in fire and debris to project outward. This again makes it unsafe for bystanders and passengers. Now, the pressure buildup and combustion from the thermal runaway can also cause structural damage to the battery housing and the vehicle itself. This results in more wasteful material and renders it difficult to recycle. So to ensure that none of these occur, battery safety has to be properly maintained. Now, there are three key components. One is correct adherence to the battery regulations, early detection of thermal runaway, and continuous monitoring with the BMS that is set to take the proper protocols once thermal runaway is detected. Now, going further into thermal runaway, there are 12 stages of thermal runaway, as written by Tran and Mankan in the review of lithium-ion battery thermal runaway modeling and diagnosis approaches. So in this review, they wrote that there are 12 steps. Now, the first step is metal ion dissolution, where the heat breaks up the crystal structure of the cathode, resulting in the migration of metal ions into the electrolyte. Then the solid electrolyte interface starts decomposing, which releases more heat, resulting in more metal ion dissolution. Reaction between the lithium and the electrolyte releases more heat, causing a chain reaction of degradation processes. And as such, the separator begins smelting. And from that, small micro internal short circuits start resulting in temperature increase due to the separator melting. Later on, the gas starts venting around here, and this increases the pressure in the battery from the gas formation. So the separator at the next stage starts melting entirely, causing a large scale internal short circuit. So it completely melts off, and this causes the large scale short circuit, which then leads to decomposition of the cathode and the electrolyte. Now, the decomposition of the cathode results in a release in oxygen, which reacts with the electrolyte and can result in combustion. Combustion of the electrolyte begins at this point, then which releases gases. And then the anode can then react with the binder material, increasing the temperature even more. And at the last stage is when the combustion can fully occur from the ignition of the gases, resulting in, again, the last point of thermal runaway. So on this scale, you'll see that the green side of this arrow on the left side is where thermal runaway cannot or can be prevented. And as it turns into red, at this point, we cannot prevent thermal runaway, and it has undergone, we can't stop it. But all throughout the green, right before the separator breakup, where it completely melts down, we can still prevent thermal runaway from happening all throughout this stage. Now, regulations currently in place in order to stop thermal runaway are the GB 38/031/2020 and the UN ECE R100. Now, both of these regulations state that the thermal runaway warning must give an alert 5 minutes prior to any hazardous conditions due to thermal propagation. So these 5 minutes means that there has to be a very early detection of thermal runaway in order for it to be for it to reduce the damage that it can cause, or even if early enough can completely prevent it. Now, in thermal runaway, there are free electrons, hydrogen, and lithium ions that are released before thermal runaway prior to the onset of deterioration due to thermal propagation. Lithium metal and lithium ion particles, which are referred in literature as dust, they contain an organic electrolyte that decomposes during thermal runaway. This organic electrolyte is comprised of a lithium salt dissolved in an organic solvent. Now we have ethylene carbonates, diethyl carbonates, and dimethyl carbonates, and the rest of this list, propylene carbonates, dimethylxylene, and gamma-butyrolactone. All of these are potential organic solvents in this electrolyte. This wide range of organic solvents can result in variations in the concentrations of the venting gas constituents, regardless of the battery chemistry. So now our sensor detects all of these ions and these particulates, and this is what we are focusing on detecting to alert before thermal runaway occurs. So we'll go, this concludes our first topic. So now we're going to go into the topic of our sensor, which again detects these ions and particulates mentioned I mentioned in the previous slide. So now this is our sensor. Our sensor shape and size can be changed due to customer requirements. It can be as small as a dime, as you can see here in the top right, with an external signal conditioning unit, or it can be all wrapped up in one package smaller than a credit card, as you can see down here. Now, this sensor detects the free electrons and ions from the battery. It can be placed at the vents, in the ducts, or within the modules, where it can get access to floating electrons. Now, the vent holes you see here allow for the free flow of the ions for detection. The sensing and conditioning circuit is located in the casing of the sensor, with a connector out here for the power that goes into the sensor, as well as the sensor signals that go out to the battery management system. The mounting fins you see right here, and the overall general design of this sensor was specifically made for our own testing rig and mounting jig. But as I said, all of this can be changed according to requirements necessary. Now, the power supply of our sensor is 12 volts DC, and it can be supplied anywhere between 9 to 24. So anywhere in that range, we can supply that kind of voltage to our sensor. So this supply voltage is boosted in the sensor circuit for the detection of the ionized gases and particulates released. The signal from the sensor circuit is then put through an amplifier to magnify the result, and then it's fed to the signal conditioner. Output from this signal conditioner ranges from 0 to 5 volts and is then outputted from the sensor and is fed into the battery management system, where further processes can be taken. So right now we'll go into the setup of of how we tested our sensors. Now, in our experimental setup method was that was used for the test was the UN GTR20 heating test. So we had a coil cooktop heater that was attached to a square beam fixed on a metal base plate. The battery pouch cell was placed on top of the heater and was fixed in place with the brackets. The setup was placed in a stainless steel container with a fireproof glass pane placed on top. Now, this entire setup was open to the atmosphere so that we attached an exhaust hood, and it was to help with clearing the gases that was produced by the battery. We had 3 thermocouples placed around the setup. Sorry. One thermocouple was placed at the, my apologies. One thermocouple was placed at the positive terminal of the battery, where it was to detect the gases that was emitting from the slits that we cut open into the battery pouch. We had another thermocouple that was placed in between the battery and the heater, and that was to give us the temperature increase of the battery. Now, the last thermocouple was placed over here on top of the entire setup to measure the atmospheric conditions around this whole test. Now, we did cut a slit into the battery pouch where we placed this thermocouple. This slit was meant to simulate an open pressure relief valve. And our sensor, located here, was placed right next to this thermocouple so that it can detect the free ions emitted from the relief valve. Now, the battery that we used in this test was an 80 amp hour battery pouch, and it was charged to 100% for this test. Now, these are our results. The entire test from the burner start to the thermal runaway was 7 minutes long. So this graph on the right here depicts the results that we got from our test. You'll see the x-axis down here is the time of the test in seconds, and we zoomed in right where the thermal runaway occurred at around 350 seconds. Now, on the top graph, you have the y-axis, which is the temperature in Celsius. The red line here is the thermocouple that was placed between the battery and the heater to give us the temperature of the battery increase. We have the blue line here. This is the thermocouple that was placed at the top of the setup to measure the atmospheric temperature. And we have this green line here. This measures the thermocouple, the temperature that was at the vent of the battery pouch. Now, on the bottom graph, we have the y-axis being voltage, and the blue line from this voltage is the battery voltage. These two purple and red lines, this is the output from our sensor on the 2 different circuits. So at the beginning of our test, we began by increasing the temperature of the burner by 35 degrees Celsius per minute. You will notice that around 230 degrees, our sensor signal shown by these 2 lines noted that it detected a bunch of ions coming out of the battery. Now, then approximately 56 seconds later, the battery voltage dropped and the temperature spiked from 250 degrees all the way up to 583 degrees, which is a 334 degree increase in about 5 seconds. The heater was then turned off when we noticed that the battery pouch was expanding. And this green plot here shows the temperature of the thermocouple placed at the vent, and you'll notice that even when our sensor was detecting the ions, there was no change in temperature for the thermocouple that was placed right next to that sensor. So we can go ahead. I'll show you the video. So we recorded all of our tests using two cameras, one recording in the visible spectrum and one in the infrared range, which is pretty much a thermal camera. And we use that to keep track of the heat progression throughout the test. Now you can see our battery pouch on the right and the sensor at the positive terminal. You'll notice that the same graph that's shown here is the one in the previous slide. And as the video progresses, this red line, you'll notice, starts detecting that there is a spike in ions. But if you'll notice in the video, there is no visible change in the battery. There is no detection. There's no gas that's showing up. But we did notice that there was a detection of ions at this point. Now, 56 seconds later, you'll notice the battery pouch expanding from the gas, and then the gas bursting, gas and fire emitting outwards, and gas filling up the entire chamber. Now, throughout this test, you'll see that our sensor, once it detected those ions, throughout the rest of the time, it keeps detecting the ions. It does not end up stopping because, again, of the slit that we have located down there. So here you notice it expanded, filled up the chamber with gas, and ignited. And that's the only point where the temperature thermocouples were able to detect a change in the temperature from the ignition of the gas. And the battery voltage drops once the battery starts expanding, which is way too late of a detection compared to when ours detected 56 seconds prior. So our next steps, our main goal is to bring our technology to markets in different areas related to battery safety and integrate our technology with companies in different sectors, not only to the automotive sector, like electric vehicles and hybrid electric vehicles, but also to the aviation sector, as well with the electric planes. We also found that there's a demand in the electric bikes and scooters as well. And even in the battery recycling sector, we found that there is a need for detection of thermal runaway, as well as in the charging of these stations. This technology could be used for even battery pack testing for design and pre-production, where it can provide more information of the deterioration of the battery and the location where the thermal runaway begins. So, as key points we'd like you to take away from this webinar, we know that thermal runaway is a propagating exothermic reaction resulting from a short circuit that deteriorates the battery and produces toxic flammable gas. To ensure battery safety, we need to follow the set battery safety regulations, have an early detection of thermal runaway, and as well maintain proper continuous monitoring with the battery management system. Now, our sensor can provide these early warnings to thermal runaway by detecting the free electrons emitted prior to the battery deterioration. Since it detects free electrons, chemistry of the battery has no effect of the capability of our sensor. And finally, to ensure optimal integration of our sensor, shape and size can all be altered based on customer requirements. Thank you.
As the next steps or how we can further explore this, we would be ready to do a POC for you where we could test this thermal runaway sensor on your products. Okay, we can look into your current technology, what you have, and based on the assessment and the customer requirement, we can conduct this testing. Okay, so we'll be happy to hear back from you. Okay, and if there are any more questions, we can also connect offline, and we can talk about this in more depth. And one more topic, okay, I'm anticipating today's audience, would be more on the battery applications. Okay, so we can have a separate technical discussion in case if we would like to deep dive into our complete battery design and engineering capabilities, all the way from cell level, module level, pack level. Okay, entire battery design and engineering development process. Okay, we can support you. Okay. So with that note, okay, we can end this webinar. I thank you everybody, okay, for joining this today's session and making this webinar, more productive.